In this video, we will see how to create a node using the LITE version of CSE. This node will be built by creating a simple FEM model describing the topology and orientation of the members, and then automatically constructing the node by choosing one of the available solutions from a node library. Using the command to add standard structures, we select a simple beam column joint from the various templates available. Member number 1 in red is the column. Member number 2 in black is the beam. We assign a material to the two members, for example S275. We select an HEB section from the archive, for example 200. And we assign it to member number 1, the column. Returning to the archive, we select an IP section, for example 220. And we assign it to member number 2, the beam. We leave the strong axis as the axis, without introducing a hinge at the end of the beam. This will therefore be a clamped node. We click OK. The system prompts us to save the model. Then a three-dimensional node is created for us to work on. This node has not yet been constructed. To do so, in the LITE version, we browse the archive to find the predefined nodes that are suitable for this type. In the version of the software used in this video, the program has selected 7 different nodes as being applicable to our node. Let's take a look at the various solutions. Since this is a clamped joint, we'll choose a node with stiffeners. We browse the images to see how the node will be built. We click OK. The list of the operations that will enable the node to be built automatically is now shown. First of all, we click OK and tell the program to build the node with the default parameters. The node has now been built. If, though, we don't like the result for some reason, if we want this plate to be thicker, for instance, then we can reset the node, reapply the macro, and tell the system to modify the parameters we want in real time, during the construction process. To modify the plate, we need to know what it is called. One way to do this is to activate the Selected Entities panel. Deselect all entities and select the plate that we want. The plate is called P1 and its current thickness is 10 mm. We reset the node to go back to the beginning. And we reapply the predefined node. Now, in the list of operations, we untick the addition of plate P1 to say that we want to edit its parameters. These are the parameter settings for this plate. In particular, the thickness is defined as a function of the thickness of member 2's flange, m2.tf. This is the formula that gave us the 10 mm value that we saw before. We can edit the formula by inserting multiplication factors or additive terms, or entering a number, such as 11, which is the thickness we want. We click OK, and the construction of the node is now complete, with its newly thickened plate. Indeed, we can see that plate P1 is now 11 mm thick. If we select a node that has already been parameterized, we can still change its parameters in order to build the nodes that we want, given the type selected. Now we are ready to run the checks. First of all, we need to decide if the default settings for checking the elements are suitable in this case. For example, let's select plate P1 only and modify it using button cell C, which stands for Selected Component. We can see that, for example, automatic FEM modeling is not selected for this plate. We'll leave these settings as they are and consider the general settings for the checks. Eurocode is set, and a series of options is available to select only the checks that we want to perform. This section is used to specify the combinations with the internal forces to be used to check the node. In the LITE version, we can add the combinations as a table by pasting the combinations from Excel tables or by typing the data in manually. Alternatively, we can opt to use a suitable fraction of the member's elastic or plastic limits, which is what we'll do now. We select member 2, which is the one that we are interested in. Suppose we do not want to compute it under compression, nor under tension. We want the shear to be 0.3 times the elastic limit along both the principal axes. There is no torsion. The moment about the strong axis is 0.3 times the elastic limit, and the moment about the weak axis is 0. This is just one of the ways to define the combinations for the checks. We save the settings. And now we run the checks. When the checks have been completed, a listing is shown with the results, which we will not discuss here. We can look at a color-coded map of the utilizations, which tells us which components have been successfully verified and which have not. In this case, all the components have been verified. If we inspect the weld utilization, the status bar at the bottom shows that this weld has a maximum utilization of 0.995 from the strength check in combination 26. As will be clear from the documentation, this combination corresponds to the shear perpendicular to the web in the horizontal beam. We may assume that these results are acceptable, Or we can alter the weld to increase the safety margin using the command shown earlier. The image shows all the welds. We can select the one we want, in green, by scrolling with the arrows, and we can adjust its thickness and hence its throat section. We can run the checks again to see what difference this has made. As we have seen, we have built and verified this node quickly in just a few clicks. Here, we have only looked at the color-coded map of the utilization envelope. Please see the dedicated lessons for full details about all the tools available for viewing and inspecting the results.